let's work on another example where we try and do an applied optimization problem, try and find a maximum or minimum in the context of some word problem. Okay, so this one is the very mathy one, a little less real world, but I think kind of an interesting one. We're building a rectangle, and we know that this rectangle has to fit underneath the curve y equals the square root of x. And we know that its base has to be on the x-axis, so this is not optional. And, I think I'm losing some words, I can't tell. Its right-hand side, I know what I want it to say. It's supposed to be sitting over here at x equals 9, so this is not optional, this is not optional. What determines the height of this thing is the fact that this corner has to just touch the curve. So I think I maybe just didn't give you enough directions, but that's what I'm wanting to say here. I'm wanting to say the bottom of the rectangle is on the x-axis, the right-hand side is on x equals 9, this vertical line, and then the top left corner has to touch the curve. So we can move this around. We could make it really short and wide, or we could move it up here and make it a lot taller, but then very skinny, and we're trying to balance those things out. Okay, so we're trying to find the rectangle with largest possible area. So once again, I'm going to say A is the area of the rectangle. So whatever you're trying to maximize or minimize, define a variable for that. And this one is actually nice and simple in the beginning. The area of a rectangle is just going to be a length times a width. So I just have to figure out how to fill those in. So let's see. This is actually given for us in the picture as well, that the left-hand corner is at x equals a. So if we want this, the base of the rectangle, we actually have all the info we need. One corner of the bottom is at 9, and the other corner is at a. So if we want to know the difference of those two, it's 9 minus a that will leave that over. So we've got 1. So we're looking for a, and I'm just going to go ahead and use that a that's in the picture. So we'll call that length. The length is 9 minus a. Okay, in that case, this is the width, and that one can be a little tricky for people. So some people are tempted to just call it y, and you could temporarily do that, but again, at some point, you're going to have to get back to a being your variable. So I would think about this again. If you choose this bottom corner, that determines the width of your rectangle, but it also determines the height of your rectangle because your rectangle has to touch this curve. So the question is, if the x-coordinate of the bottom corner is a, what is the y-coordinate of the top corner? Or whatever, the x-coordinate of the top corner is a. And the answer is that's determined by this. That's exactly what this says. Whatever your x is, your y is the square root of that. So the height of this rectangle is going to be the square root of it. And that's our formula, and that's actually fairly simple, but I think I am going to go ahead and think about this as an a to the 1/2 and distribute just to make my derivative even easier. So we'll say the a is 9a to the 1/2 minus a to the 3/2. We have to add exponents there. All right, and then I think I'm going to sidetrack and think about endpoints right now instead of at the very end. So reasonable domain here, a is our variable, so the smallest a could be and make sense in this problem is 0. So I'm going to say 0 is one of my endpoints. It's a terrible choice. Your rectangle flattens out completely, but we're looking for extremes, endpoints, right? And then the biggest a could be is 9. That flattens your rectangle out as well, but those are the extremes in this problem. So I'm going to need to check a of 0 at some point and a of 9, and let's see if we can find any critical values as well. So now I'm ready for a derivative. Find your critical values. So I get 9/2 a to the negative 1/2 minus 3/2 a to the positive 1/2 equals 0. So this is the same as a 9/2 root a. You don't have to rewrite them as roots, but I think sometimes it's easier for people to see what happens. So I don't know. I'm going to go ahead and move this to the other side. 3/2 square root of a. And then I'm going to clear fractions. So I'm going to multiply both sides by 2 root a. You don't have to move this to the other side before you clear fractions. And I'm just going to be left with a 9 on this side. Here, the 2's cancel, So I have 3 times root A times root A. Root A squared is just an A, so I'm getting A equals 3 as my one and only critical value. Okay, so we need to plug all of these in to make sure we're hoping that this gives us our maximum area. We need to plug in and check. So back to our area formula. Actually, I kind of like this version of it, the factored version for plugging in. When A is 0, this is 0, so the whole thing is 0. The a to the 1/2 multiplied by kills everything. When A is 9, little a, the first factor is 0, which makes everything 0. And we saw that in the picture, flat this way, both of those have 0 area. So A equals 3 is looking pretty promising. We have 9 minus 3, which is 6, and then we have the square root of 3. So this is definitely my max. And then once again, just make sure at the very end, kind of a lot of steps, at the very end, go back and reread and make sure you're giving what you were asked for. So this was find the dimensions. So I have this, which is an area, but it's not dimensions. The dimensions are 9 minus a and square root of a. So it's actually just those two separately, but still, we want to write this as 6 by the square root of 3. It's the base is 6, its height is the square root of 3. So that is my actual final answer. All right, thanks for watching.